The universe was once too hot for anything but lonely atoms. Then came the cosmic dawn, a quiet revolution where the first complex molecules sparked into existence. This is the story of chemistry's very first breath, the moment the stage was set for everything that followed, including you. We are going on a journey to explore 30 mind-bending theories about how those primordial molecules came to be. By the end, you will understand the cosmic recipes that may have written the first lines in the story of life itself. We will see how dust grains became tiny laboratories and how exploding stars might have forged our biological blueprints. What do you think was the universe's very first step towards building life? To find the birthplace of chemistry, we must look into the cold, dark voids between the stars. This is where the first theory begins, with a concept you might have heard of, but on a cosmic scale. It is called the primordial soup, but this is not a warm pond on a young Earth. This is a primordial soup in space, a vast, frigid cloud where the ingredients for life began to simmer. After the Big Bang, as the universe expanded and cooled, the simplest atoms began to link together. Hydrogen bonded with oxygen to form water. Nitrogen latched onto hydrogen to create ammonia. Carbon found hydrogen to make methane. These were the universe's first recipes, written in the language of atomic attraction. But these simple molecules were adrift, lonely in an immense emptiness. They needed a place to meet, to concentrate, and to react. That place was found on the surfaces of microscopic dust grains, specks of silicon and carbon floating within vast interstellar clouds. In the deep cold of space, these grains became sticky traps. Water vapor, ammonia, and methane molecules drifting by would freeze onto their surfaces, building up layer by layer into icy mantles. Picture a grain of cosmic sand covered in a frost of potential. This icy coating was not just a blanket, it was a cosmic laboratory, a solid-state reactor where chemistry could happen in slow motion. Shielded within these icy matrices, the simple molecules were held in place, neighbors for millions of years. Then energy arrived. Cosmic rays, high-energy particles from distant supernova, would pierce the cloud. Ultraviolet light from newborn stars would bathe the grains. This constant drizzle of radiation did not destroy the ices, it energized them. The radiation could break molecular bonds, creating highly reactive fragments, radicals, desperate to form new connections. When two of these excited fragments sat next to each other on the grain's surface, they could link up, forming something new, something more complex. A water and ammonia molecule might be transformed. A carbon chain might begin to grow, over eons in countless dark clouds across the galaxy. This slow, cold chemistry could have produced a zoo of organic molecules, the precursors to amino acids and sugars. Then, when a shockwave from a nearby star burst compressed the cloud, these dust grains, with their precious cargo of complex frost, could have been incorporated into new solar systems. They would become part of comets and asteroids, which then rained down on young planets like Earth, delivering the pre-made ingredients for life. So the first theory suggests our biological story did not start in a pond, but in the frozen depths of space on a speck of dust waiting for a spark. These icy mantles were only the final product, however. The true magic began on the bare surface of the grain itself, a stage set long before the frost arrived. Within those dark molecular clouds, trillions upon trillions of microscopic specks drift like cosmic sand. Each one is a world in miniature, a silicate or carbon flake no wider than a wavelength of light. They seem insignificant, but these dust grains are the universe's first chemical factories, and their assembly line is a principle called surface catalysis. Picture a single hydrogen atom, the most abundant thing in existence, hurtling through the void. It is incredibly reactive, desperate to find a partner to form stable hydrogen gas. But when two hydrogen atoms collide in open space, they simply bounce apart. the reaction needs a third body to absorb the excess energy of their union, a witness to their marriage. That witness is the dust grain. When a lonely hydrogen atom strikes the grain's surface, it doesn't just ricochet away. It sticks, wandering across the landscape of atoms that make up the grain. Soon, another hydrogen atom lands nearby. Now, instead of a fleeting high-speed collision in empty space, they are neighbors held in place on a solid stage. The grain's structure acts as a catalyst, subtly tweaking the electric fields around the atoms and providing a platform that soaks up the reaction's energy. The bond forms, a molecule of hydrogen gas is born, and it gently drifts back into the cloud. This is how the most fundamental molecule in the cosmos was forged, not in the fire of the Big Bang, but on the cold, solid surfaces of dust. And hydrogen was just the start. The same process worked for more complex unions. A carbon atom and an oxygen atom, adrift and unreactive on their own, could meet on a grain. With the catalytic help of the surface, they could link, forming carbon monoxide. Add hydrogen atoms and you might get formaldehyde, a simple organic molecule. These grains provided a haven where the chaotic dance of atoms could become a coordinated waltz, lowering the energy barrier so that chemistry could proceed in the profound cold of deep space, where temperatures hover just above absolute zero. Without these microscopic platforms, the universe might have remained a soup of lonely atoms. But dust grains gave them a place to meet, to shake hands, and to build the first fragile bridges toward complexity. So the second theory reveals the unsung hero of cosmic chemistry, a speck of dust that is, in essence, the universe's first laboratory bench. Yet even dust grains do not work in isolation. They are the workers, but they need the right factory, a protected environment vast enough for an entire chemical industry to arise. That factory is a giant molecular cloud, a cosmic nursery so immense it defies human comprehension. Picture not a wispy cirrus cloud in Earth's sky, but a mountain range in space, light years across and containing the mass of 1 million suns. These are the coldest, densest places in the modern galaxy. And within their shadowy hearts, the universe's molecular diversity explodes. The sheer scale of these clouds is their first gift to chemistry. Their outer layers, buffeted by starlight, are turbulent and harsh, but deep inside, the density of gas and dust becomes so thick it acts as a cosmic blanket, shielding the interior from the destructive ultraviolet radiation that tears molecules apart elsewhere in space. In these dark, quiet cores, temperatures plunge to just 10 degrees above absolute zero. It is a deep freeze that paradoxically enables creation. Here, atoms and simple molecules collide more frequently, held together longer by the cold. And on the countless dust grains suspended in this frigid fog, the surface catalysis we discussed can proceed for millions of years without interruption. This is where the simple becomes complex. Radio telescopes peering into clouds like Taurus or Orion have not just found water or carbon monoxide, they have detected a staggering chemical zoo. Alcohols like methanol and ethanol float in these voids. Simple acids like formic acid are present. Astronomers have even found the fingerprints of glycolaldehyde, a simple sugar molecule that is a direct building block for ribose, a key component of RNA. These are not just random compounds, they are the very types of molecules that, on a young planet, would readily link up to form the foundations of life. The cloud itself becomes a vast, slow-motion reactor. Shockwaves from newborn stars rumbling through the cloud can compress regions, heating the dust grains momentarily and allowing ices on their surfaces to melt and mix, triggering new rounds of chemical reactions. When those stars finally ignite, their winds and radiation will eventually blow the cloud apart, seeding the surrounding space with this rich organic harvest. So the third theory shows us that before the first star in a nebula even shone, the cloud that birthed it was already cooking the ingredients for biology. The nursery was not just for stars, it was a kitchen where the universe prepared its most profound recipe. But how do we know such complex chemistry is even possible in the cold vacuum of space? The answer comes from a famous experiment performed in a laboratory on Earth over 70 years ago. In 1952, a young chemist named Stanley Miller, working under his advisor Harold Urey, sought to test a revolutionary idea. Could the conditions of the early Earth have sparked the building blocks of life? They built a simple glass apparatus, filling it with water, methane, ammonia, and hydrogen, gases thought to mimic our planet's primordial atmosphere. Then they added a spark, simulating the energy of ancient lightning. Within just days, the clear water turned a murky reddish-brown. Analysis revealed a stunning result. The experiment had produced amino acids, the organic molecules that are the fundamental components of proteins and, by extension, all living cells. It was a landmark moment, proving that under the right conditions, the leap from simple chemistry to the precursors of biology was not only possible but probable. Now take that same brilliant logic and project it onto a cosmic canvas. The fourth theory asks, what if the Miller-Urey experiment is not just a story of Earth's past but a universal process? What if the vast nebulae of space are themselves gigantic, natural versions of that iconic glass flask? Instead of a small pool of water, picture an ocean of molecular gas light years across. Instead of methane and ammonia from a lab bottle, these are the raw materials frozen onto dust grains or floating freely. And crucially, instead of a man-made electrical spark, the energy comes from the universe itself. The cosmic rays that constantly streak through the galaxy, the intense ultraviolet radiation blazing from newborn stars, the titanic shockwaves rippling out from supernova explosions, these are not destructive forces in this context. They are the cosmic equivalent of Miller's spark. When a blast of ultraviolet light or a high-energy cosmic ray particle slams into a simple molecule like formaldehyde or hydrogen cyanide drifting in a cloud, it doesn't just obliterate it. It breaks the molecular bonds, shattering it into highly reactive fragments and radicals. These charged, desperate pieces are like the atoms in Miller's chamber after the spark, primed for new connections. In the dense confines of a nebula, they immediately collide with other fragments or intact molecules. In this chaotic, energetic dance, they recombine not randomly, but following the same rules of chemistry that operated in that Chicago laboratory. The result could be the direct formation of amino acids like glycine or nucleobases like adenine, the letters of the genetic code, all synthesized in the deep freeze of interstellar space. Telescopes have already found hints of this. The spectral signature of glycine, the simplest amino acid, has been tentatively identified in several comets and around star-forming regions. It suggests that the universe, long before planets even exist, is already running its own version of the Miller-Urey experiment on a galactic scale, using starlight and stellar explosions as its spark. So this theory proposes that the ingredients for life are not a rare planetary accident, but a common cosmic product, written into the very laws of physics and chemistry that govern the nebulae where stars are born. Yet these cosmic factories faced a critical delivery problem. How did the complex molecules forged in the cold clouds and energized nebulae find their way to a warm, wet planet like Earth? The answer may lie in the most dramatic period of our solar system's history, and a theory that transforms wandering space rocks from destructive forces into vital carriers. This is the idea of panspermia, but with a crucial twist. We are not talking about fully formed microbes surviving an interstellar journey. We are talking about molecular panspermia, the delivery of the raw chemical ingredients for life. After the Sun and planets formed, the young solar system was a chaotic construction site filled with leftover debris. Comets, asteroids, and meteoroids, countless in number, carried within them a frozen record of that primordial cloud. Many were rich in water ice, and locked within that ice, a menagerie of organic compounds created by the very processes we have explored. These bodies were not sterile. They were preloaded with the universe's chemistry kit, Then, around 4 billion years ago, a gravitational reshuffling of the giant planets sent a cataclysmic storm of this debris hurtling inward. This period, known as the Late Heavy Bombardment, saw millions of these objects pummel the inner planets. From our perspective, it looks like an era of apocalyptic violence. But from the perspective of a carbon atom waiting to become part of something alive, it was the greatest delivery service in history. A comet, for instance, is a perfect vessel. Its icy nucleus acts as a deep freeze container, preserving fragile organic molecules for billions of years. As it approaches the sun, only the outer layers vaporize into the spectacular tail, while the interior remains pristine and protected. When such a body struck the early Earth, the impact energy was immense, but not uniformly destructive. While the point of impact was vaporized, vast amounts of material from the comet's outer regions were thrown into the atmosphere or fell as debris over a wide area. Laboratory experiments simulating these impacts show that a significant fraction of the complex organic molecules, even delicate amino acids, can survive the shock. They are not incinerated, but rather gently cooked and scattered. Imagine a cosmic seed pod hardened to survive re-entry, cracking open upon a fertile new world. Each impactor became a seeding event, raining down not just water, but also methanol, formaldehyde, and perhaps even the blueprints for nucleobases. The Earth's early oceans, therefore, may not have needed to build these molecules from scratch through slow, planetary-scale chemistry. Instead, they could have been filled by a steady, billion-year drizzle of pre-made ingredients from space, a rich broth concentrated by evaporation in tidal pools and hydrothermal vents. This theory suggests that our planet was not a solitary kitchen, but a recipient in a galactic catering event. The first steps toward life on Earth might not have been first steps at all, but a continuation of a chemical process that began in the dark heart of an interstellar cloud, with the final delivery made by a speeding comet under a sky filled with fire. But the journey from a simple molecule like formaldehyde to a genetic sugar is not a single leap. It is a chain reaction, a domino fall of chemistry that might have been written into the cold clouds of space. Formaldehyde is a deceptively simple molecule, just one carbon atom, one oxygen atom, and two hydrogens. Yet its discovery in interstellar space was a revelation, a clear signal that organic chemistry was already at work far from any planet. Its significance lies in its reactivity, a kind of molecular eagerness that makes it a perfect building block. In the presence of a basic catalyst, something as simple as a mineral-laden dust grain or even a water-ice surface, formaldehyde molecules do not remain solitary. They begin to link up to form a slightly larger molecule, then another attaches and another. This process, known on Earth as the Foremost reaction, is like a game of molecular Lego where every piece is identical, yet they snap together to create increasingly complex structures. The end products of this spontaneous chain reaction are sugars, including ribose, the 5-carbon sugar that forms the structural spine of RNA. RNA is more than just a messenger. It is widely considered a potential candidate for the very first self-replicating molecule, the spark of genetics itself. So this theory proposes an astonishing possibility. The frigid clouds between the stars, peppered with dust grains coated in formaldehyde ice, could have been vast, slow-motion sugar factories. When bathed by the gentle energy of cosmic radiation or warmed by a passing shockwave, these ices could have undergone foremost-like chemistry right there in the void. The necessary catalysts, minerals like silicates or carbonates, were already present as part of the dust grains themselves, and the water required for the reaction was frozen in abundance alongside the formaldehyde. The result would not have been a pure batch of ribose, but a messy primordial syrup of different sugars and related molecules, a tarry organic residue clinging to the grains. When those grains later aggregated into comets and asteroids, this sticky, sugar-laden coating would have been incorporated, frozen in time for millions of years. Upon delivery to a young world like Earth, melting in a warm tide pool or a hydrothermal system, this cosmic syrup would have been ready to interact with other prebiotic molecules, like the amino acids also delivered from space. It provides a direct link, a plausible chemical pathway from the most abundant complex organic molecule found in space all the way to a core component of the genetic system. The universe, it seems, may not have just delivered the letters for life's code, but also the sugary paper on which that first code was written. Sugar chains and amino acids are profound discoveries, but they are not the only complex architecture gracing the cosmos. Drifting through the interstellar medium, astronomers have found the spectral signatures of something even sturdier, a class of molecules so tough and so abundant they are considered a fundamental component of interstellar dust. These are polycyclic aromatic hydrocarbons, or PAH. Picture them not as simple chains, but as flat, chicken wire-like sheets of carbon atoms arranged in interlocking hexagonal rings with hydrogen atoms fringing the edges. They are essentially microscopic flakes of soot, the same basic structures found in candle smoke or car exhaust, but on a cosmic scale. Their detection across the galaxy is staggering. They are estimated to account for up to 20% of all the carbon in the Milky Way. This sheer abundance marks them as prime candidates for being among the universe's first major complex molecules. Their stability is their superpower. The fused ring structure makes them incredibly resilient, able to withstand the harsh ultraviolet radiation that would tear simpler molecules apart. When a photon of starlight hits a PAH, the energy is distributed across its entire network of rings, like a ripple spreading across a pond, rather than concentrating on a single weak bond. This allows it to vibrate and re-radiate the energy as infrared light, which is precisely how we detect them without breaking apart. This durability meant PAHs could survive and accumulate over eons, even in environments where other organics were destroyed. But they were not just inert survivors, they were active construction sites. The edges of these carbon sheets are where the chemistry happens. Each ring at the perimeter is missing a bond, capped instead by a reactive hydrogen atom. In the dense, cold environment of a molecular cloud, these hydrogen atoms could be knocked off by a cosmic ray or a UV photon, creating a bare, chemically sticky carbon site on the edge of the sheet. Now, imagine a floating nitrogen atom or an oxygen-bearing molecule drifting by and latching onto that open spot. Step by step, atom by atom, the simple PAH could be functionalized, gaining new chemical groups like ammonia or hydroxyls. These additions would transform it from a passive flake of soot into a reactive platform, a kind of molecular scaffold. Further reactions could build outward from these points, creating three-dimensional structures. Some scientists theorize that under the right conditions, with the addition of nitrogen and other elements, PAHs could even form the basic frameworks for nucleobases, the information-carrying molecules of DNA and RNA. Think of them as the universe's original Lego bricks, not the finished model, but the sturdy, interlocking base plates. Billions of these tiny, stable platforms, forged in the furnaces of dying stars and spread across galaxies, could have provided the perfect foundation upon which the more delicate chemistry of life could later assemble. They offered the cosmos a durable template, a resilient starting point from which the fragile dance of biology could eventually begin. The resilience of PAHs reveals a cosmos already rich with complex carbon, but where did these molecules ultimately settle? To find the nursery where chemistry truly became planetary, we must look at the birthplace of worlds themselves. Around every newborn star, a vast, swirling disk of gas and dust takes shape, a protoplanetary disk. This is not a passive cloud, but a colossal, dynamic chemical reactor spinning in the vacuum of space. Within its elegant spiral arms, the fate of molecules is decided by a single, powerful variable: distance from the star's fiery heart. The temperature gradient across the disk is staggering. Close in, where the young sun's radiation is fierce, temperatures soar high enough to vaporize ice and even melt rock. Here in this hot, mineral-rich zone, chemistry takes on a fiery character. Tiny silicate dust grains, the same stuff that makes up sand on a beach, are not just spectators. Their crystalline surfaces, heated and activated, become exceptional catalysts. Imagine these grains as tiny, searing hot plates. When simple gases like carbon monoxide and nitrogen swirl past, they can stick to these hot surfaces and undergo reactions impossible in the cold of deep space. This region could forge hardy, refractory organics, molecules built to withstand heat, perhaps laying the groundwork for the carbon chemistry that would later emerge on rocky, inner planets like our own. Venture further out, just beyond what astronomers call the snow line, and the environment transforms. Here, temperatures plummet. Water that was vapor closer to the star now freezes solid onto every dust grain, creating thick, icy mantles. This is the domain of cold chemistry we explored earlier, but now supercharged by the disk's density and motion. Formaldehyde, ammonia, and hydrogen cyanide freeze into these icy layers. Cosmic rays and stellar radiation still penetrate, driving complex reactions in the ice. But the disk adds a new ingredient: constant mixing. Turbulence and eddies in the swirling gas can transport grains from the cold outer regions inward toward the warmth, briefly thawing their icy coatings and allowing a new round of liquid phase chemistry before they cycle back out and refreeze. This freeze-thaw cycle, repeated over millennia, is like a cosmic stirring of the pot, encouraging molecules to link in ever more complex ways. In the far, frigid reaches of the disk, where comets and icy asteroids form, the chemistry preserves the most volatile and delicate compounds, a frozen archive of the cloud's original organic bounty. This theory paints a profound picture. The raw materials that clump together to form planets are not chemically uniform. A pebble destined for the hot, inner solar system carries a different molecular legacy than a snowball destined for the outer darkness. Earth may have been seeded primarily by material from the warmer, drier regions inside the snow line, while comets delivered a separate, frozen cocktail from the outer disk. Our planet's first oceans and atmospheres were thus a blend of distinct cosmic recipes, each prepared in a different zone of the same magnificent stellar kitchen. But where does the energy come from to stir this cosmic kitchen? Starlight cannot penetrate the deepest, densest parts of a molecular cloud. The answer arrives not as light, but as a relentless, invisible rain of atomic bullets. Cosmic rays are protons and atomic nuclei accelerated to nearly the speed of light by supernova explosions and other violent events. They are the universe's ultimate high-energy particles, and they can go where photons cannot. These tiny, hypervelocity projectiles slice through the vast emptiness of space and punch deep into the hearts of the darkest molecular clouds. When one of these particles collides with a simple molecule like molecular hydrogen or carbon monoxide drifting in the cloud, it does not just bump it aside. It delivers a devastating blow, tearing an electron from the molecule in a process called ionization. The result is a molecular ion, a charged and wildly unstable fragment. This ion is now a chemical desperado, missing an electron and desperate to regain stability by stealing one from any neighbor it encounters. This single event sets off a cascade. The newly formed ion reacts with a neutral molecule, transferring its charge or breaking the other molecule apart to form new reactive radicals. Those radicals then attack other molecules, and a chain reaction of gas phase chemistry ignites. In the profound, cold, and near vacuum of a cloud, where atoms might drift for centuries without meeting, these ionization events create localized hotspots of frantic chemical activity. They provide the activation energy needed for reactions that would otherwise be frozen in time, too slow to ever build anything significant. This process can build complexity directly in the thin gas, not just on dust grains. For instance, a cosmic ray could ionize a helium atom, which then transfers its charge to carbon monoxide. That ionized carbon monoxide can then react with hydrogen to eventually form hydrocarbon chains, the backbones of more complex organics. It is a domino effect of destruction leading to creation. Without this constant, penetrating drizzle of high-energy particles, the interiors of these stellar nurseries might remain chemically inert, a quiet soup of simple molecules. Cosmic rays are the agitators, the match strikers in the cosmic dark. They ensure that even in the most shielded, frozen recesses of a nebula, the alchemy of molecule building never fully sleeps, driven by the distant, echoing thunder of exploding stars. Cosmic rays are not the only source of disruptive energy in a nebula. A far more visible power also sculpts the chemical landscape, ultraviolet light from massive, brilliant stars. This radiation is so intense it can rip molecules apart in a flash, a process called photodissociation. Yet within that destructive power lies a profound creative force. At the illuminated boundaries of dark molecular clouds, where starlight meets shadow, ultraviolet photons perform a delicate act of cosmic surgery. They do not simply obliterate, they dissect. A single UV photon carries exactly the right energy to strike a water molecule and precisely sever the bond between its hydrogen and oxygen atoms. The result is not just destruction, but the creation of two highly reactive fragments, a hydrogen atom and a hydroxyl radical. These are not peaceful particles, they are chemical sparks, charged with unused bonding potential and desperate to find new partners. The same process happens to carbon monoxide, breaking it into carbon and oxygen atoms and to molecular hydrogen, splitting it into two lone hydrogen atoms. This creates a seething, energetic soup of radicals right at the cloud's edge, a zone astronomers call a photodissociation region. Here, the chemistry is frantic. A carbon atom produced by a split-second photodissociation might, within a millisecond, slam into an hydroxyl radical clinging to a nearby dust grain. On that solid surface, their frantic energy is absorbed, and they bond, forming carbon monoxide again, or perhaps something new like formaldehyde if other atoms are present. Alternatively, in the thin gas itself, an oxygen atom from a shattered water molecule could meet a carbon monoxide ion and form carbon dioxide. The ultraviolet light is essentially performing the first, crucial step in an assembly line. It breaks the sturdy, simple molecules of the cosmos down into their reactive components. Then, in the dense environment of the cloud boundary, those components immediately recombine, but not always back into what they were. They form new, more complex alliances. This is why the illuminated rims of nebulae, like the famous Horsehead Nebula, glow with such intricate colors and host a rich variety of molecules. The UV radiation from nearby hot stars is not sterilizing the area, it is forging a chemical forge, driving reactions that would be impossibly slow in the calm, dark core. It suggests that the very radiation we consider deadly to life might have been the essential chisel that carved the first complex structures from the raw stone of primordial gas. Ultraviolet light carves the edges of nebulae, but for a truly explosive burst of chemistry, the universe relies on its most cataclysmic events. The shockwave from a supernova is a force of unimaginable power, a supersonic wall of energy and matter blasting outward at tens of millions of kilometers per hour. When this titanic wavefront slams into a neighboring molecular cloud, it does not gently nudge it. It delivers a sledgehammer blow of cosmic proportions. The cloud material is violently compressed, squeezed to densities thousands of times greater than before. In that instant of compression, the gas heats to phenomenal temperatures, soaring from near absolute zero to thousands of degrees in a flash. This is not a slow, steady cooking process. It is a sudden, searing forge. For a brief, brilliant moment, the cold, simple molecules of the cloud are plunged into a maelstrom of extreme heat and pressure. Under these hellish conditions, chemical bonds that were stable for eons are shattered. Atoms are ripped from their molecular homes and thrown into a frenzied, chaotic dance. But as the shockwave passes and the compressed gas rapidly expands and cools in its wake, something remarkable happens. The frantic atomic particles, now a superheated soup, begin to recombine. In that critical cooling phase, they do not simply revert to their original, simple forms. The intense energy of the event opens reaction pathways that are closed in the cold quiet of a normal cloud. Atoms find new partners, carbon, nitrogen, and oxygen linked together in novel, more robust arrangements. Think of it as the universe's pressure cooker. The sudden, immense pressure forces ingredients together that would normally never react, and the intense heat provides the energy to weld them into something new. In the cooling ejecta of the supernova itself, and in the shocked, enriched material of the cloud, astronomers have detected the signatures of complex molecules like silicon carbide and even fullerenes, the famous soccer ball-shaped carbon cages known as buckyballs. These are molecules forged in fire, not cold. A single such stellar explosion could thus perform two vital functions. First, it scatters the heavy elements like carbon, oxygen, and iron forged in the star's core across interstellar space. Second, in the very act of its death, it uses its final, furious energy to weld those new elements into hardy, complex molecular structures. These molecules, now embedded in the expanding debris and the reshaped cloud, become part of the next generation of stars and planets. So a supernova is not just an end, it is a violent, creative rebirth. It seeds the galaxy not only with the raw elements of life, but with some of its first complex architectural pieces, forged in a heartbeat of stellar fury. Supernova forge molecules in fire, but the universe's most patient chemistry unfolds in the profound cold. Deep within the hearts of the largest molecular clouds, conditions reach an almost unimaginable stillness. Temperatures here plummet to just 10 degrees above absolute zero, a point where molecular motion nearly ceases. In this frozen quiet, something remarkable happens. Cold becomes an architect of complexity. The theory of cold chemistry proposes that this extreme chill is not a barrier to creation, but its essential catalyst. With all thermal energy sapped away, atoms and simple molecules lose their frantic bounds. They move with a slow, drifting languor. When they encounter one of the countless dust grains suspended in this dark fog, they do not ricochet away. Instead, they stick, van der Waals forces and hydrogen bonds latching them onto the grain's surface like cosmic Velcro. One by one, over millennia, layers accumulate. Water freezes into place. Carbon monoxide, formaldehyde, ammonia, and methanol all join the frosty deposit. A single dust grain becomes a tiny, layered snowball, an icy mantle that can be hundreds of molecules thick. This mantle is not a uniform sheet of ice. It is a stratified chemical archive, a frozen record of the cloud's history. The first molecules to freeze, like water, form the bottom layers. Later arrivals, like carbon monoxide or nitrogen, freeze on top. Each layer is a snapshot of the cloud's changing composition over millions of years. Within this solid-state matrix, the molecules are not dead. They are held in a frozen embrace, their positions fixed but their potential immense. The deep cold is key. It suppresses destructive thermal vibrations and holds the reactant molecules in close, intimate proximity for eons, something impossible in a warm, chaotic gas. Then a spark arrives, a cosmic ray, one of those high-energy particles from a distant stellar explosion, pierces the dark core. It tunnels through the icy mantle, leaving a tiny, energized trail in its wake. Or perhaps a stray ultraviolet photon, born in a star far outside the cloud, manages to penetrate this deep. When this energy is deposited into the ice, it doesn't just warm it. It breaks specific molecular bonds. A water molecule might be split into a hydrogen atom and a hydroxyl radical. Two neighboring formaldehyde molecules might have their bonds rearranged. The crucial point is this: in the solid ice, the reactive fragments produced by the radiation cannot float away. They are trapped, caged in place by the frozen lattice around them. They vibrate, they tunnel through microscopic quantum pathways, but they remain essentially neighbors. This allows for slow, deliberate reactions that would be fleeting in a gas. Over thousands of years, a hydroxyl radical might find a carbon monoxide molecule a few atomic positions away and link up to form formic acid. Hydrogen atoms might add to a carbon chain, building it link by link. The ice itself acts as a protective matrix and a three-dimensional template, guiding these cold chemical reactions toward increasingly complex organic molecules, even amino acids or the precursors to sugars. This process is achingly slow by our standards, but given the millions of years these cloud cores exist, it has all the time in the universe. Eventually, the gravitational balance of the cloud core tips. It begins to collapse under its own weight, destined to form a new star and planets. As it collapses, the material spirals inward and friction causes temperatures to rise. The icy mantles on the dust grains begin to warm to sublime, turning from solid directly into gas. In this great thaw, all the complex organics painstakingly assembled over eons within the ice are released into the swirling protoplanetary disk. They become part of the raw material for new worlds, so the darkest, coldest places in the galaxy are not chemical deserts. They are silent, frozen laboratories where time itself is the main ingredient, and cold is the quiet force that builds the future. This molecular handedness is called chirality, and it is one of biology's deepest enigmas. Every amino acid that builds the proteins in your body exists in two mirror image forms, left-handed and right-handed, like a pair of gloves. In a purely chemical experiment, you would always get a perfect 50-50 mix of both. Yet life on Earth uses almost exclusively the left-handed versions for its amino acids and the right-handed versions for its sugars. This universal preference, this homochirality, is a fundamental signature of life. The question is, did this bias arise from a random chance on our young planet, or was the deck subtly stacked from the very beginning out among the stars? The 13th theory suggests the cosmic kitchen may have had a preference. One compelling idea points to a distant, violent beacon, a pulsar. These rapidly spinning neutron stars emit not just regular light, but intensely focused beams of circularly polarized light. This light twists as it travels, spiraling either to the left or the right. If such a beam from a nearby stellar remnant happened to sweep through a cloud rich in probiotic molecules, it could have acted as a cosmic filter. The twisted radiation would interact slightly differently with the left and right-handed versions of a molecule, preferentially breaking down one mirror image over the other. Over millions of years, this could create a small but significant excess of one-handedness in the cloud, an imbalance frozen into the ices on dust grains. Another possibility lies closer to home in the protoplanetary disk itself. Dust grains are not just random lumps. Many have crystalline structures with chiral surfaces, like certain forms of quartz. As simple organic molecules drift down and stick to these surfaces, the atomic landscape of the crystal might favor the formation or stabilization of one-handedness over its mirror image. It is like trying to fit a left hand into a right-handed glove. The fit dictates the outcome. A magnetic field flowing through the cloud or disk could further influence these interactions, adding another layer of bias. The resulting excess would not be 100%, perhaps just a 1% or even 0.1% more left-handed amino acids than right. But that is all it would take. When those biased materials were delivered to Earth via comets and asteroids, they seeded the primordial soup with a slight tilt. Then, on the planet, that tiny imbalance could have been dramatically amplified through a process called autocatalysis, where molecules of the preferred handedness help create more copies of themselves. What began as a faint cosmic whisper became a biological shout. This theory offers a profound shift in perspective. The handedness of life, a defining feature of every living thing, might not be a terrestrial accident. It could be a fossil, a lasting imprint of starlight from a dead star, or the subtle geometry of ancient dust, written into our very chemistry before Earth was even born. The universe's preference for left or right might be subtle, but its talent for building intricate carbon architecture is not. Among the most stunning molecular structures ever discovered in space are fullerenes, often called buckyballs. These are not simple chains or sheets, but perfect hollow cages of carbon atoms. The most famous, C60, consists of 60 carbon atoms arranged in a pattern of hexagons and pentagons, forming a sphere that looks exactly like a microscopic soccer ball. For decades, these molecules were a laboratory curiosity, synthesized on Earth in the 1980s. Then, astronomers found their unmistakable spectral fingerprints in the most unexpected of places, the diffuse gas between the stars and, astonishingly, in the dusty shrouds surrounding dying red giant stars. This discovery was a revelation. It meant the cosmos was not just making carbon chains, it was weaving carbon into resilient, three-dimensional geodesic domes on a molecular scale. Theorists now believe these cosmic masterpieces form in the violent, carbon-rich atmospheres of aging stars. As a red giant nears the end of its life, it pulsates, shedding its outer layers in powerful stellar winds. In this expanding shell of gas, conditions are just right for carbon atoms, abundant from the star's own fusion processes, to link up. In the searing heat and turbulence, they do not just form sooty flakes of pHs. Instead, under the right pressures and temperatures, they can self-assemble into these closed, cage-like structures. The formation is a kind of cosmic origami, where a flat sheet of carbon curls in on itself and stitches its edges together, creating a perfectly sealed sphere. The stability of a buckyball is its superpower. Its closed, symmetrical structure distributes stress evenly, making it incredibly resistant to radiation and physical shock. It can survive the brutal journey through the interstellar medium, from the dying star to a nascent planetary system, essentially intact. But its role may be far more active than that of a simple survivor. That hollow interior is a shielded chamber, a potential nanoscale reaction vessel. Picture a buckyball drifting through a molecular cloud. Its cage-like structure could, in theory, trap a smaller atom or molecule inside, like helium or even a simple organic compound during its formation. This guest molecule will be caged, protected from the destructive ultraviolet radiation that floods space. Inside this carbon cocoon, the captive molecule could be held in an unusual state, or even catalyze reactions on the inner wall of the cage itself. Some scientists speculate that these carbon cages could act as molecular taxis, safely transporting fragile probiotic compounds across the galaxy. More intriguingly, the buckyball's exterior, with its unique geometry of bonds, could itself act as a catalyst. Its curved surface might provide the perfect template to attract and orient other floating molecules, facilitating their linkage into more complex chains right there in the void. The discovery of fullerenes in space forces us to expand our vision of cosmic chemistry. The universe is not merely producing the ingredients for life, it is forging sophisticated, durable containers for them, tiny armored cars speeding through the galactic highways, possibly safeguarding the very reactions that would one day lead to biology. The search for glycine is a cosmic detective story with profound implications. Glycine is the smallest and simplest of the 20 amino acids that form the proteins essential to all known life. Finding it in space would be like discovering a single, specific Lego brick from a scattered, galaxy-wide set, proving that at least one of life's fundamental building blocks can be made without biology. The hunt has been long and contentious. For years, tantalizing hints came from meteorites that fell to Earth, like the Murchison meteorite, which contained small amounts of glycine. But the critical question remained, was this amino acid forged in space, or could it have been contaminated after landing on our planet? To settle the debate, scientists needed to detect glycine out there in the wilds of the cosmos. The first major claim came from the European Space Agency's Rosetta mission, which spent 2 years orbiting comet 67P Churyumov-Gerasimenko. Its Rossiner instrument, a sophisticated mass spectrometer, sampled gases streaming from the comet's icy nucleus. In the complex data, scientists believed they saw the clear signature of glycine. More importantly, they detected it alongside other precursor molecules like methylamine and ethylamine, suggesting a logical chemical pathway for its formation right there in the comet's ices. This was powerful evidence, but comets are part of our solar system, a local environment. The ultimate prize would be finding glycine in the vast interstellar medium, the space between stars where it would be truly universal. Here, the evidence is even more debated. Radio astronomers scan the sky, looking for the unique rotational signature of glycine molecules tumbling in cold clouds. Several teams have reported possible detections in massive star-forming regions like Sagittarius B2, a turbulent cloud near the galactic center, yet each claim is met with intense scrutiny. The problem is complexity. Glycine has many rotational lines, and in the crowded radio spectrum of a dense cloud, other more abundant molecules can emit at very similar frequencies. Distinguishing the faint whisper of glycine from the cosmic background noise is like trying to hear a single violin note in a roaring symphony. Skeptics argue the detected signals could be from other, simpler organic molecules. Proponents counter that the pattern of multiple lines matches glycine's predicted fingerprint. If the interstellar detections are ever confirmed beyond doubt, the implications would be monumental. It would mean that the universe, using only the cold chemistry of dark clouds and the energy of starlight, routinely manufactures a direct component of proteins. This would strongly suggest that the raw materials for life are not a rare planetary accident, but a common product of galactic evolution. The galaxy could be filled with molecular clouds quietly assembling these biological precursors, seeding every new planetary system with the same starter kit. The debate itself reveals a deeper truth. The frontier of astrochemistry is pushing into ever more complex territory, moving from simple chains to the very molecules that stitch our bodies together. The elusive signal of glycine, whether finally confirmed or not, represents our quest to answer one of humanity's oldest questions. Are the ingredients of life written into the fabric of the cosmos itself? The dust grains drifting through those ancient clouds were not blank slates. Each microscopic speck carried a geological history written in its atomic structure. These were not just lumps of carbon, but tiny crystals of minerals like olivine and pyroxene, forged in the atmospheres of earlier generations of stars. Their crystalline surfaces were not smooth, but landscapes of atomic-scale mountains and valleys, ridges and pores. This specific mineralogy, the 16th theory proposes, did far more than just provide a sticky surface. It actively directed the chemistry happening upon it, like a foreman on a molecular assembly line. Think of a catalytic converter in a car. Its honeycomb interior is coated with precious metals like platinum and palladium. These metals have surfaces that are uniquely good at grabbing exhaust molecules, breaking them apart, and reassembling them into less harmful gases. Cosmic dust grains may have performed a similar primordial function. A silicate mineral like olivine has a repeating pattern of silicon and oxygen atoms, with magnesium or iron tucked in between. This creates a charged, orderly surface. When a simple molecule like carbon monoxide or formaldehyde freezes onto that surface, it doesn't just stick at a random angle. The electric charges and geometric arrangement of the crystal lattice can force the molecule to orient itself in a specific way. It pins it down, presenting one part of the molecule outward and making a particular chemical bond more vulnerable or more accessible. This precise positioning is everything. It means that when the next reactant molecule drifts in and freezes alongside the first, they are not just two neighbors on an ice rink. They are held in the optimal position for a specific reaction to occur. the mineral surface effectively templates the assembly, guiding which atoms link to which. One type of silicate might be particularly good at lining up formaldehyde molecules to start that sugar-forming chain reaction. Another, rich in iron oxides, might excel at shuffling nitrogen into the mix, encouraging the formation of nitrogen-bearing compounds like ammonia or hydrogen cyanide, which are crucial for making amino acids and nucleobases. The influence could go even deeper into the realm of molecular handedness. Some minerals are themselves chiral, their crystals growing in left or right-handed spirals. A molecule landing on such a surface would find itself in an environment that is intrinsically lopsided. It might fit more comfortably or react more readily in one mirror image configuration than the other. A left-handed crystal face could, over eons of cold chemistry, produce a slight excess of left-handed organic molecules, directly imprinting the geology of the dust onto the biochemistry of the future. This means the type of star that produced the dust and the specific conditions in its cooling atmosphere could have predetermined what kind of organic chemistry its debris would later foster in the clouds of space. The universe's first complex molecules may not have been random products of chance encounters, but the directed offspring of crystalline dust, with stardust itself holding the blueprints for life's earliest structures. The idea that life began with RNA presents a compelling puzzle, but its pieces may have been scattered across the galaxy. The terrestrial RNA world hypothesis suggests that before DNA and proteins, a simpler world existed where RNA molecules handled both information storage and chemical catalysis, acting as the first self-replicators. Yet the leap to such a complex molecule on early Earth seems vast. A cosmic perspective shrinks that gap dramatically. This theory proposes that RNA did not have to be invented from scratch on our planet. Instead, its core components could have been forged in separate stellar factories, delivered, and only later assembled into that first fragile chain. Consider the three parts of an RNA nucleotide. The sugar, ribose, is a product of the foremost reaction, a chain linking of formaldehyde molecules we already know occurs on icy dust grains. The phosphate backbone finds its source in minerals like schrebersite, a phosphorus-rich compound commonly found in iron meteorites, which reacts readily with water to release soluble phosphates. Then there are the nucleobases, the information-carrying letters like adenine and guanine. How could such intricate, nitrogen-rich rings form in space? Laboratory experiments provide a stunning answer. When scientists recreate the icy mantles of interstellar grains, a mix of water, ammonia, methanol, and hydrogen cyanide frozen at near absolute zero, and then bathe them in ultraviolet light, something remarkable happens. Upon warming, the ice yields adenine, one of the four key nucleobases of both RNA and DNA. The basic chemistry of cosmic ices, energized by starlight, appears perfectly capable of writing the first letters of the genetic alphabet. This means the recipe for RNA's ingredients was likely written into the cold clouds of the Milky Way. Ribose sugars formed in foremost reactions on grain surfaces. Nucleobases like adenine synthesized within irradiated ice mantles. Phosphorus-bearing minerals condensed in the disks around young stars. Each component followed a different cosmic pathway, accumulating over eons in separate reservoirs. The final act of assembly, however, required a more forgiving environment. When comets and asteroids carrying these disparate ingredients bombarded the early Earth, they deposited their cargo into a dynamic planetary setting. Warm tidal pools, hydrothermal vent systems, or wet-dry cycling clay beds could have provided the perfect crucible. Here, the cosmic ribose could have linked with the meteoritic phosphate and the nebula-synthesized adenine, finally zipping together into the first short strands of RNA. The immense leap from chemistry to genetics, therefore, might not have been a single improbable event on one planet. It could have been the inevitable conclusion of a billion-year process that started in the dark between the stars, with the universe patiently preparing each piece of the puzzle until they finally found a place warm and wet enough to snap together. The universe's recipe for complexity did not end in the cold clouds of space. It continued in the turbulent skies of young worlds, where a different kind of organic alchemy was brewing. On the hazy orange moon Titan, the Cassini spacecraft revealed a landscape stained a deep, rusty red. This color comes from Tholin's thick, tarry polymers that are not a single molecule, but a vast, complex mixture of organic compounds. They form when simple gases like methane and nitrogen are zapped by ultraviolet sunlight or cracked by electrical energy, their broken pieces recombining into ever larger, more intricate chains that eventually become this reddish sludge. Titan shows us this process in action today, but the 18th theory suggests it was a universal phenomenon in the youth of countless planetary systems. Picture the primordial atmospheres of the early gas giants, Jupiter and Saturn, in their first 100 million years. They were not the relatively clear, banded giants we see now. They were likely shrouded in thick, reducing atmospheres, rich in methane, ammonia, and water vapor swirling in global storms. In those tempestuous skies, lightning flashes of unimaginable scale would have ripped through the clouds. The constant bath of ultraviolet light from the young, active sun would have poured in. Just as on Titan, this energy would have shattered the simple molecules, sparking a frenzy of gas-phase chemistry that built tholins layer upon layer. These were not delicate compounds. Tholins are remarkably hardy, resistant to further breakdown. They would have formed in immense quantities, coating cloud particles in a sticky, organic haze. Eventually, gravity would take over. These complex polymers would clump together, becoming heavy enough to begin a slow, eternal rain down into the deeper, hotter layers of the atmosphere. But some might never reach the core. In a system still crowded with leftover planetesimals, colossal impacts were common. A major strike on a moon like Europa or Callisto, or even a glancing blow to the gas giant's upper atmosphere itself, could have ejected plumes of this organic-laden material right back into space. Tholin-coated ice fragments could have been flung across the solar system, some spiraling inward toward the terrestrial planets. This paints a startling picture. The early Earth, coalescing in the inner solar system, may have been seeded not only by pristine organics from comets, but also by these more processed, complex tars from the outer planetary factories. These tholins raining into our own early atmosphere or landing in the oceans would have delivered a rich, pre-made cocktail of hydrocarbons and nitrogen-bearing organics, a kind of cosmic starter culture that could have dissolved and interacted to form the building blocks for life. The process suggests that anywhere in the galaxy with a world possessing a thick, reducing atmosphere and an energy source from a fiery young star to intense planetary lightning, could become a prolific producer of complex organic matter, potentially showering its entire celestial neighborhood with the rudimentary ingredients for biology. The stormy atmospheres of gas giants are not the only alien kitchens cooking complex organics. Far from the sun's warmth, in the frozen outer reaches of a solar system, an entirely different recipe unfolds in perpetual darkness. Beneath the icy crusts of moons like Jupiter's Europa or Saturn's Enceladus, global oceans of liquid water are thought to churn against a rocky seafloor. Where that mineral-rich rock meets the warm, salty water, we find a cosmic echo of one of Earth's most fertile environments, the deep-sea hydrothermal vent. On our planet, these vents are oases of life, powered not by sunlight but by chemosynthesis, a process where microbes derive energy from chemical reactions between the hot vent fluids and the cold seawater. The theory suggests these alien seafloors could be performing the same alchemy, building complexity in the dark. As seawater percolates down through cracks in the rocky mantle, it is heated by the moon's internal warmth, perhaps from tidal flexing or radioactive decay. This superheated water becomes a potent solvent, leaching minerals like iron, sulfur, and nickel from the rock. When this mineral-laden, alkaline fluid erupts back into the cold ocean through porous vent chimneys, it creates a sharp gradient in temperature, acidity, and chemistry. This gradient is a potent source of chemical-free energy, a driver for reactions. The vent structures themselves, built of porous minerals like sulfides and silicates, provide vast labyrinthine surfaces perfect for catalysis. Here, in the eternal night and crushing pressure, simple molecules like carbon dioxide or methane dissolved in the water could be coaxed into linking together. The mineral catalysts could facilitate the formation of acetic acid or pyruvate, key metabolic intermediates. Over geological timescales, this steady, mineral-driven chemistry could generate a diverse soup of organic compounds, from amino acids to fatty acids, all synthesized in the complete absence of starlight. This idea profoundly expands the cosmic address for life's ingredients. It means a warm, rocky core interacting with a liquid water ocean is a standalone biochemical factory, a closed system that needs no external energy from a star. The building blocks for life could be simmering in the subsurface abyss of countless icy worlds throughout the galaxy. Their dark oceans not barren wastes, but potential chemical crucibles waiting for a spark. Hidden within the chemical bonds of a simple water molecule lies a cosmic clock, a natural fingerprint that tells us exactly where and when that molecule was born. This is the story of deuterium fractionation, and it transforms chemistry into detective work. Deuterium is a heavy cousin of the common hydrogen atom. Its nucleus contains not just a proton, but also a neutron, making it about twice as heavy. In the warm, bustling environment of a planet or a nebula close to a star, this tiny weight difference doesn't matter much. Hydrogen and deuterium get mixed together fairly evenly in molecules. But in the profound, motionless cold of a dark interstellar cloud, where temperatures hover just above absolute zero, that extra mass becomes everything. Chemical reactions in that extreme cold are exquisitely sensitive to mass. A deuterium atom, being heavier, forms a slightly stronger bond than a regular hydrogen atom. In the slow-motion dance of atoms on a dust grain, when a molecule has a choice between grabbing a hydrogen or a deuterium atom, the stronger bond with deuterium is ever so slightly favored. Over millions of years, this tiny preference gets amplified. The icy mantles that build up on grains in these clouds become enriched, packed with deuterium far beyond the normal cosmic abundance. It is a process that stamps a clear, indelible label on anything formed there, made in the deep freeze. Now imagine a comet, a frozen relic from the solar system's birth. When scientists analyze the water ice in that comet, they can measure the ratio of deuterium to hydrogen. If that ratio is sky-high, it is a smoking gun. That water and any organic molecules locked within it did not form in the warm inner solar system. It is a pristine, unaltered sample of the ancient interstellar cloud that collapsed to form our sun and planets. This is not just theory, we have the evidence. The water in many comets, like the famous 67P studied by Rosetta, has a deuterium fraction several times higher than Earth's oceans. Even more telling, complex organic molecules extracted from primitive meteorites, like the Murchison meteorite, show the same dramatic deuterium enrichment. Certain amino acids and sugars within these space rocks carry the heavy hydrogen signature in specific patterns that rule out contamination on Earth. They bear the frozen mark of the cloud. This means we are not just guessing that interstellar chemistry can build complexity, we are holding the proof in our hands. These molecules, with their extreme deuterium content, are cosmic fossils. They are time capsules that survived the violent formation of the solar system, the fiery plunge through an atmosphere, and a crash landing on our world, all while preserving the chemical conditions of their birth. By reading this deuterium fingerprint, we can sort the truly ancient interstellar ingredients from those cooked up later in the protoplanetary disk or on a young planet. It tells us that the universe's first complex molecules are not lost to time. They are here, embedded in stones that fall from the sky, waiting to tell us their story of a birth in the dark, cold cradle of the galaxy. While deuterium acts as a chemical fingerprint, another invisible force may have been directing the cosmic assembly line itself. Across the vast expanses of the galaxy, woven through every nebula and dark cloud, are interstellar magnetic fields. These are not the simple bar magnet fields you might recall from school, but immense, diffuse structures, lines of force stretching for light years. They are incredibly weak by Earth standards, thousands of times fainter than a common refrigerator magnet, but their scale is everything. In the near-perfect vacuum of space, even this faint whisper of a field can exert a profound influence on the smallest charged particles. And in the molecular clouds where our story unfolds, cosmic rays and starlight are constantly creating just such particles, ions. When a cosmic ray strips an electron from a molecule of hydrogen or carbon monoxide, that molecule is no longer neutral. It becomes a charged ion, suddenly sensitive to the magnetic environment. Picture these newly charged molecules not as passive drifters, but as tiny compass needles. Each one begins to spiral along the invisible magnetic field lines like beads on a cosmic wire. This guided motion changes everything about how chemistry proceeds in the cloud. Instead of a purely random, chaotic dance, the movement of key reactants gains a subtle direction. The magnetic fields could funnel ions along specific pathways, concentrating them in particular regions of the cloud. One area might become enriched with carbon-bearing ions, while another gathers a surplus of oxygenated molecules, creating specialized chemical zones within a single nebula. This concentration effect would make certain reactions far more likely, simply by bringing the necessary ingredients together more efficiently. But the influence could be even more precise, touching on the very handedness of life's molecules. A chiral molecule, one that comes in left and right-handed mirror images, can interact slightly differently with polarized light or magnetic fields. As these nascent chiral molecules form on dust grains and are then released into the cloud, the weak interstellar magnetic field could act as a gentle filter. It might slightly favor the drift or stability of one mirror image over the other, creating a small but widespread bias across an entire star-forming region. This bias, imprinted while the molecules are still adrift in space, could then be frozen into cometary ices and delivered to planets, providing that initial tilt that biology later amplified. So magnetic fields add a layer of elegant order to the apparent randomness of cosmic chemistry. They suggest the universe's first complex molecules were not just thrown together by chance in a dark cloud, but were subtly guided, sorted, and even selected by the same fundamental forces that sculpt the galaxies themselves. The gentle drift of dust grains and the quiet cold of molecular clouds are not the only sources of the galaxy's organic wealth. For a more urgent, fiery kind of chemistry, we must look to the final breaths of sun-like stars. In their luminous, dying years, these stars become asymptotic giant branch stars, bloated and brilliant. Those rich in carbon become especially important cosmic chemists. Their outer atmospheres are vast, turbulent, and cooling as they expand into space. Here, in the stellar wind itself, a rapid and prolific form of gas phase chemistry takes flight. As the hot gas from the star's surface billows outward, it expands and cools dramatically. In this dynamic environment, carbon atoms liberated by the star's own fusion processes are abundant. They do not travel alone for long. In the cooling flow, these carbon atoms eagerly link with each other and with other available atoms like hydrogen, cyanide, and oxygen. The conditions are perfect for building carbon chains and rings right in the gas before any dust has even had a chance to form. Astronomers have detected a menagerie of molecules in these stellar outflows, including hydrogen cyanide, carbon monoxide, and even the simple hydrocarbon acetylene. But the real surprise is the detection of more complex species like polycyclic aromatic hydrocarbons, those sturdy carbon sheets, and fullerenes, the carbon cages. This suggests the stellar envelope acts as a high-speed factory, assembling robust organic architectures in a matter of years or decades, not the millennia required in a dark cloud. Then the star's powerful wind does the delivery work. It sweeps this freshly synthesized, complex carbon material directly off the production line and blasts it into the surrounding interstellar medium. Each dying star of this type becomes a fountain, spraying its organic harvest across light years. This contribution is immense, seeding the raw material for future molecular clouds and eventually new planetary systems with a rich inheritance of pre-made complexity. So while cold clouds are the patient libraries of cosmic chemistry, these stellar outflows are the prolific publishers, constantly writing new organic chapters and distributing them to the galaxy at large. Our solar system's unique chemical blueprint was written during a single, violent act of creation. The pre-solar nebula, that vast, spinning cloud of gas and dust from which everything we know emerged, was far more than just raw material. It was a colossal, stratified chemical reactor, and its brief, fiery transformation determined the destiny of every future world. As gravity pulled the cloud inward, it did not collapse evenly. It flattened into a furious, whirling disk with a dense, hot core where our sun was igniting and a frigid, expansive outer region. This created a dramatic gradient, a cosmic spectrum of conditions from forge to freezer. Close to the infant sun, temperatures were searing. Here, only the most resilient materials could survive. Metals and silicate minerals remained solid, but so did a class of hardy, carbon-rich molecules known as refractory organics. These are complex chains and rings that can withstand incredible heat without breaking apart, likely forged earlier in the nebula's own hot inner zones or inherited from ancient stellar outflows. This region became the chemical province of the future rocky planets Mercury, Venus, Earth, and Mars. Their building blocks were baked in this inner furnace, rich in metals and these tough, heat-resistant carbon compounds, but largely stripped of volatile ices and delicate organics. Move just a little farther out, past an invisible boundary called the frost line, and the environment shifted. Temperatures dropped enough for water vapor to freeze into solid ice grains. This was a chemical tipping point. Suddenly, water ice became a major building block, dramatically increasing the amount of solid material available to clump into planets. But the chemistry here was still active, influenced by the sun's fierce radiation and the disk's turbulent mixing. This zone, where asteroids and the cores of the gas giants likely formed, became a mixing bowl. It contained both the refractory materials from the inner disk and a growing abundance of ices, allowing for a richer variety of organic chemistry, especially where liquid water could exist temporarily on warm, rocky bodies. Now journey to the distant, dark reaches of the disk. Here, in the perpetual shadow far from the proto-sun, temperatures plunged to near absolute zero. This was the deep freeze, where not just water, but carbon dioxide, methane, and ammonia all solidified into icy mantles on dust grains. In this profound cold, the delicate, volatile organic molecules synthesized in the earlier molecular cloud, like formaldehyde and hydrogen cyanide, could survive intact. They were not cooked or processed by stellar heat, they were simply archived, frozen in time. This region became the reservoir for comets and the icy moons of the outer planets. Each comet nucleus is a time capsule, holding the unaltered chemical recipe of the solar system's outermost factory floor. This theory explains why a meteorite from the asteroid belt and a sample from a comet are chemically distinct siblings. They are not made of the same stuff because they were born in different neighborhoods of the same cosmic city, each with its own local industry. The violent mixing during planet formation did blur some lines as gravitational kicks sent material careening across the disk, but the broad chemical heritage was locked in place during that brief, dynamic 100 million years. Our Earth, then, did not form from a uniform soup. It aggregated from material that originated primarily in that warm, dry zone inside the frost line, material pre-loaded with refractory organics and life-essential minerals. The delicate, volatile ingredients from the outer disk, the sugars and nucleobases, had to be delivered later by comets and asteroids sent on chaotic journeys inward. So the solar system we inhabit is not a random assortment of rocks and ice. It is a chemically ordered structure, a fossilized gradient of heat and cold, with each planet and comet carrying the specific molecular legacy of its birth address in that primordial, spinning disk. Phosphorus presents a cosmic paradox. It is absolutely essential for life as we know it, a key component of the backbone of DNA, the energy currency of cells called ATP, and the phospholipids that make up cell membrane. Yet across the vast chemistry of the interstellar medium, phosphorus is notoriously scarce and stubborn. While carbon, hydrogen, oxygen, and nitrogen weave themselves into countless complex forms, phosphorus seems to be a reluctant participant, creating a potential bottleneck for the emergence of biology on any world. The question becomes, how did a young planet like Earth acquire enough of this critical element in a usable form to spark life? The answer may lie in two very different cosmic delivery systems. One theory looks to the skies of giant planets. In the reducing, hydrogen-rich atmospheres of worlds like Jupiter, theoretical models suggest that simple phosphorus-bearing molecules like phosphine could form. Phosphine is a pyramid-shaped molecule of one phosphorus atom and 3 hydrogens. It is toxic to us, but in the context of prebiotic chemistry, it represents a rare, volatile carrier of phosphorus that could be lifted high into a gas giant's atmosphere. From there, colossal impacts or atmospheric escape could potentially seed the surrounding protoplanetary disk with this precious element. An even more dramatic source is the fury of supernova. The titanic shockwaves and intense neutron fluxes in these stellar explosions are thought to be primary cosmic forges for many heavy elements, including phosphorus. The violent conditions could directly synthesize phosphorus compounds or embed phosphorus atoms into dust grains that later become part of molecular clouds. Yet, finding phosphorus in space is one thing, delivering it to a rocky planet in a reactive, bioavailable form is another. This is where a second, more grounded theory provides a compelling answer. Within a certain class of meteorites, the iron meteorites, lies a peculiar mineral called schreibersite. It is an iron-nickel phosphide, a metallic, silvery mineral that forms in the cooling cores of asteroid-sized bodies. To a geologist, it is a curiosity. To a probiotic chemist, it is a potential master key. Schreibersite has a remarkable property. When it comes into contact with water, it does not simply dissolve. It corrodes in a very special way, releasing phosphorus not as a boring phosphate rock, but in a suite of highly reactive, oxygen-sensitive compounds called phosphites and hypophosphites. These molecules are far more chemically lively than the phosphates typically found in Earth's crust. In laboratory experiments that simulate the conditions of early Earth, when chunks of schreibersite-bearing meteorite are placed in warm water, they steadily leach these reactive phosphorus compounds into the solution. And in that solution, something magical can happen. The reactive phosphorus readily links up with other organic molecules that might be present, like the ribose sugars or nucleobases delivered by comets, to form organophosphorus compounds. These are the direct precursors to the molecules like ATP and the links in the DNA chain. So this theory paints a vivid picture. The early Earth, after its formation, may have had very little accessible phosphorus locked in its crustal rocks. The element was trapped in insoluble minerals, biologically useless. Then, during the late heavy bombardment, a rain of iron meteorites fell from the sky. Each impact was not just a flash of destruction, but also a delivery of Schreibersite-rich metal. As these meteoritic fragments weathered in the planet's first oceans and lakes, they acted like slow-release capsules, steadily dispensing reactive phosphorus into the primordial soup. This could have created localized hotspots, ponds or tidal zones rich in this crucial, life-enabling element, effectively removing the bottleneck. The phosphorus in your very cells, driving your energy and holding your genetic code, may not be of this Earth at all. It might be the gift of an ancient asteroid, a piece of a shattered protoplanet that fell from the heavens to water the chemical garden of life. The universe may not have needed a single, perfect cradle for its first molecules. Instead, the grand diversity of cosmic chemistry suggests a more chaotic and democratic origin. This is the stochastic theory, where chance and necessity work hand in hand across the galaxy. Stochastic simply means random or probabilistic, a process governed by the roll of cosmic dice. Here, the emergence of the first complex molecules was not a linear, directed event, but a sprawling, messy experiment run in a million different laboratories simultaneously. In this view, no one environment could have created everything needed for life's precursors. The harsh, radiant envelopes of dying stars were perfect for forging sturdy polycyclic aromatic hydrocarbons, those resilient carbon sheets. The deep, silent freeze of a molecular cloud's heart was the only place gentle enough to assemble delicate amino acids within icy mantles. The turbulent boundaries of nebulae bathed in starlight might have been the exclusive forge for certain sugars. Each location in the galaxy, with its unique blend of temperature, density, and energy, became a specialist, producing its own signature brand of organic molecule. These products did not stay in their birthplaces. The galaxy is in constant slow motion. Stellar winds blew the sooty pHs from red giants into the void. Shockwaves from supernova mixed cloud material from different regions. Gravity pulled disparate streams of gas and dust together to form new molecular clouds, each one a melting pot of pre-made ingredients from across light years. Over billions of years, the interstellar medium became a vast, simmering soup where the specialized products of countless stellar factories and cloud nurseries were stirred together. This is where chance takes the lead. A dust grain coated in amino acid-rich ice from one cloud could, through a random gravitational encounter, be flung into a region rich in the sugary residues from another. A comet forming in the outer reaches of a new solar system would not gather material from one source, but would be an aggregate, a snowball made from the mixed debris of an entire galactic neighborhood. Its nucleus would be a chaotic archive, a jumble of every type of prebiotic molecule the local cosmos had to offer, frozen in a single, dirty ice ball. The final, fateful step required a planetary stage. When such a comet or a shower of meteorites with varied origins bombarded a young, wet world like Earth, it delivered not a single pure ingredient but the entire cosmic pantry at once. In the warm tidal pools or hydrothermal vents, these randomly assembled sets of molecules, products of a billion different chance events across space and time, were finally brought into close and constant contact. Here, in a stable environment with liquid water and mineral catalysts, the stochastic lottery of the galaxy met the necessity of chemistry. The molecules that could react did. The chains that could stabilize grew. What began as a scattered, random production across the cosmos became concentrated, focused, and tested in a planetary crucible. Life, then, might not be the product of one brilliant recipe, but the inevitable outcome of a universe so vast and so chemically prolific that it eventually, somewhere, mixed every ingredient in the right bowl. Even the deepest voids of space were never truly empty of energy. From every direction, in every cubic centimeter of the universe, comes a faint, cold whisper of light, the cosmic microwave background radiation. This is the cooled and stretched afterglow of the Big Bang itself, a relic from a time when the cosmos was a seething, opaque fireball. Today, it is a frigid bath of microwaves just a few degrees above absolute zero. But rewind the clock, and this universal backdrop transforms into a potent player in our story. In the first few 100 million years after the Big Bang, the universe was smaller and denser, and the CMB was correspondingly hotter, its photons carrying more energy. While still not as violent as ultraviolet starlight or cosmic rays, this radiation was a gentle, pervasive warmth that permeated every corner of the nascent cosmos. It was everywhere, a universal energy source available to the very first wispy clouds of hydrogen and helium that were beginning to coalesce. In those primordial clouds before the first stars ignited to provide more intense light, the CMB would have been the primary source of photons. Its gentle, omnipresent glow could have performed a crucial, subtle function, photochemistry. A photon from the CMB, striking a simple molecule like molecular hydrogen or the first tentative lithium hydride, could have provided just enough energy to nudge an electron into a higher state or to break a weak bond. This would not have been the explosive, high-yield chemistry of later eras. It would have been a slow, patient simmer, a low-level activation that kept simple chemistry ticking over across the entire universe. Imagine a vast, dark room warmed by a single, faint radiator. It is not enough to cook a meal, but it is enough to prevent everything from freezing solid, to allow slow processes like curing or fermentation to begin. The CMB acted as that universal radiator. It ensured that even in the profound isolation of the first gas clouds, atoms and molecules were not completely inert. They were subtly energized, primed for the more dramatic chemistry that would come when the first stars finally switched on and flooded the cosmos with ultraviolet light. This theory suggests that molecular evolution did not have to wait for the brilliant dawn of the first galaxies. It could have begun in the cosmic twilight, gently coaxed along by the fading heat of creation itself, a whisper from the Big Bang that stirred the first ingredients in the dark. The cosmic dust that seeded our chemistry may have done far more than just carry ingredients. It might have built the very stage upon which life would later play. This theory flips the script entirely. Instead of complex molecules simply forming in the calm of a nebula, they could have been active, essential architects in the violent construction of planets themselves. Picture again those microscopic dust grains, but now focus not on their chemistry, but on their physics. In the protoplanetary disk, these grains are constantly colliding, a silent, endless blizzard. For planets to form, these tiny specks must stick together, growing from dust to pebbles to boulders to mountain-sized planetesimals. But there is a problem. Bare silicate or carbon grains are like microscopic billiard balls. When they collide, especially at higher speeds, they are just as likely to shatter or bounce apart as they are to stick. Gravity is useless at this tiny scale, so growth should stall. This is the great filtration problem of planet formation, how to cross the gap from dust to gravel. The answer may have been clinging to the grains all along, the sticky, organic mantles. After eons of chemistry in the molecular cloud, these grains were not bare. They were coated in thick, tarry layers of complex organics, polymers similar to the tholins we see on Titan. This was not a smooth frost, but a sticky, viscous sludge. Now imagine two such grains colliding in the disk. Instead of a hard, brittle impact, it is more like two snowballs or two pieces of chewed gum smacking together. The organic gunk acts as a shock absorber, dissipating the energy of the collision. More importantly, it acts as a glue. The complex, polymerized tars are physically sticky, like cosmic tar pits on a microscopic scale. When grains touch, their organic coatings merge and intertwine, holding the grains together far more effectively than the weak van der Waals forces between bare minerals ever could. This organic glue dramatically lowers the barrier for growth. Collisions that would have led to destruction now lead to permanent mergers. Dust grains become fluffy, porous aggregates, their surfaces perpetually sticky, eagerly capturing the next grain that drifts by. This process, known as coagulation, could have been supercharged. What might have taken millions of years with bare grains could have accelerated into a much shorter time frame, allowing pebbles to form before the swirling gas of the disk dissipated. These organic, rich pebbles would then be the fundamental building blocks clumping into planetesimals, the embryos of future worlds. The implication is staggering. The very same complex molecules that would later become the feedstock for biology, the amino acids and sugars, were first serving a vital mechanical function. They were the construction material, the cosmic mortar that allowed the bricks of the solar system to hold together. Without this sticky organic glue, planet formation might have been too slow or too inefficient, leaving behind only rings of fine dust. The worlds that did form, like Earth, would have been built from material already preloaded with life's potential, their very rocks infused with the tarry residues of cosmic chemistry. So life's precursors were not passive passengers on a random journey. They may have been active participants, the indispensable midwives that helped birth the rocky, watery planets that would one day become their home. The idea that our cosmic ancestors might have had a guiding hand is a profound leap in the narrative of our origins. Theory 28, directed panspermia, ventures into this speculative territory. It suggests the first complex molecules, or perhaps even the earliest living cells, did not arise by chance on Earth or in a random nebula. Instead, they were deliberately planted here, a biological seed sent across the interstellar void by an ancient, advanced civilization. This is not the random scattering of organic matter by comets, but a targeted delivery, a purposeful act of cosmic gardening. While firmly on the fringe of mainstream science, the concept is seriously discussed in certain corners of astrobiology and philosophy because it forces us to confront the deepest questions of our place in the universe. Could life be so rare or so fragile in its initial spark that a past civilization sought to spread it? Or conversely, could it be so common that spreading it is a natural, even inevitable, activity for any intelligence that survives its technological adolescence? Proponents of directed panspermia point to the apparent speed with which life emerged on Earth. The planet cooled enough for liquid water roughly 4.4 billion years ago. The earliest fossil evidence for microbial life appears shockingly soon after, by 3.8 billion years ago. That is a geological blink of an eye, a window of only a few 100 million years. To some, this suggests the starting materials, or even the first self-replicating systems, were already highly advanced when they arrived. They imagine a scenario where a passing interstellar probe, perhaps a relic from a civilization long since gone, surveyed our young, wet planet and released a payload of engineered microbes or complex organic templates perfectly suited to thrive here. The delivery system would be indistinguishable from a natural comet or asteroid, its artificial origin hidden in plain sight. This theory fundamentally reframes the search for complex molecules in space. It is no longer just a quest to understand natural chemistry. It becomes a potential search for signatures of intelligence, for a message or a product that bears the hallmarks of design. If we were to discover a molecule in a distant nebula with an impossibly complex structure, or one that serves no apparent function in abiotic chemistry but is perfectly optimized as a genetic precursor, it could raise startling questions. Are we looking at a masterpiece of natural selection across cosmic timescales, or at the artifact of a distant mind? Directed panspermia, for all its speculative nature, serves a vital philosophical purpose. It challenges our assumption of cosmic loneliness and our view of life as a purely local accident. It suggests that the chain of causality leading to you and me might be far longer and more mysterious than we ever conceived, stretching not just back to a star's death or a cloud's collapse, but perhaps to a conscious decision made under the light of another sun, billions of years ago. The molecules we seek, then, might be more than just chemicals. They could be the first chapter in a story we are only beginning to read, a story written not just by physics, but by a potential legacy we have yet to understand. But what if the universe's prolific chemistry is not a promise but a trap? The cosmos seems to be a master at producing complex organic molecules, from amino acids in comets to sugars in dark clouds. Yet when we look out at the silent, starry expanse, we see no signs of other civilizations. This contradiction is the heart of the Fermi paradox, the haunting question of where everybody is. One unsettling answer is known as the Great Filter, a hypothetical barrier so difficult to cross that it prevents most life from advancing to intelligence. And the 29th theory places this filter not on distant planets, but right here, in the very chemistry we have been celebrating. It proposes that while the universe is brilliant at cooking the ingredients, it might be spectacularly bad at assembling them into the meal of life. The transition from a rich soup of complex molecules to a simple, self-replicating, evolving system could be the universe's rarest event. Think of all the pathways we have explored. Ultraviolet light on Titan makes thick tholins, radiation in ice creates tarry residues, polymers form readily, gluing dust grains together. But what if that is the problem? Chemistry might have a strong tendency to run downhill into stability, not uphill toward complexity. Most organic reactions, when left to their own devices, do not create delicate, replicating RNA strands. They create goo, they make inert glues, stable tars, and insoluble gunk. These are molecular dead ends, chemically stable tombs where carbon gets locked away for eternity. A pond on a young planet might not be a nurturing broth. It might be a tar pit where delivered organics quickly polymerize into a sticky, lifeless sludge under the sun's rays. The leap from chemistry to biology requires something extraordinary. It needs molecules that can not only copy themselves, but do so with occasional, heritable mistakes, allowing for evolution. It needs a system that can escape chemical equilibrium, that can draw energy from its environment to keep building order instead of succumbing to disorder. The universe's default settings seem to favor the latter, the descent into stable, dead tars. So the filter may be this, the spontaneous emergence of a molecular system that can walk the tightrope between stability and mutability, between a crystal's perfect order and a tar's chaotic mess. It is a needle-thin path through a maze of chemical possibilities, and most worlds, no matter how rich in organics, likely get lost in the labyrinth. Their complex molecules, instead of becoming a genesis, become a funeral shroud, locking away their potential forever. This theory reframes our entire search. Finding amino acids in a meteorite is not a sign that life is inevitable. It might simply be evidence of the first, easy step on a journey with a near-impossible next step. The silent galaxy around us, then, might not be empty of ingredients. It could be filled with worlds that are organic rich, yet biologically barren, their oceans stained with the colorful, complex tars of a chemistry that never quite made the leap. The final theory shatters the frame entirely, asking us to step outside our own universe. We have traced a path of cosmic chemistry that seems almost destined, from carbon chains in dark clouds to amino acids in comets, all leading to the life we know. But what if this entire story is just one chapter in an infinitely larger book? This is the perspective of the multiverse. If our cosmos is just one bubble in a frothing sea of universes, each with its own unique set of physical laws and fundamental constants, then the very idea of a first complex molecule becomes wildly unpredictable. In our universe, carbon is the champion of complexity. Its four bonding hands allow it to form long, stable chains and intricate rings, the perfect scaffold for biology. Water is the miraculous solvent, its polarity and temperature range ideal for dissolving and shuffling the molecules of life. But tweak a single constant, the strength of the nuclear force or the mass of an electron, and the entire cosmic recipe book is rewritten. In another universe where temperatures are perpetually scorching or pressures are unimaginably dense, silicon might take carbon's throne. silicon sits right below carbon on the periodic table, sharing its 4 bonding tendency. In our world, silicon's bonds with oxygen are so strong they form rocks, locking it away in inert crystals. But in a hotter, more energetic reality, those bonds might be just right for forming complex, flexible silicon-based polymers, a geology that is alive. In a frigid universe where water is forever frozen solid, lakes of liquid ammonia or methane could serve as the universal solvent, hosting a slow, alien biochemistry where reactions unfold over millennia. The first complex molecules in such a place would be unrecognizable to us, not based on the sugars and amino acids we seek, but on silanes and azides, forming crystalline structures or oily films that think and evolve. This theory does not invalidate our search, it contextualizes it with breathtaking scale. It suggests that the 30 pathways we have explored, from dust grains to supernova, are not the only roads to complexity. They are simply the roads paved by our universe's particular physics. Our cosmic chemistry, for all its wonder, might be a local dialect in a galaxy of languages. The profound takeaway is this: either our universe is exquisitely fine-tuned for carbon-based life, making our existence a rare and precious fluke in the multiversal desert, or the parameters for some kind of complex, self-organizing chemistry are surprisingly broad, and the cosmos is teeming with biologies we cannot even begin to imagine. As we close this journey through 30 theories, we are left not with a single answer, but with a humbling and exhilarating vista. The quest to find the universe's first complex molecules is more than a detective story about our past. It is a mirror held up to reality itself, asking what is possible, what is necessary, and just how strange and beautiful the foundations of existence might truly be. From the silent chill of a dark cloud to the fiery death of a star, we have traced a universe tirelessly building its own future. It begins with a lonely atom, finds a partner on a speck of dust, and grows into chains and rings under the glow of starlight or the shock of a supernova. These are not just chemical reactions, they are the first whispers of a story that would one day become us. We have seen dust grains become tiny laboratories, their icy mantles cradling amino acids. We have followed comets as cosmic couriers, delivering pre-made ingredients to young planets. We have pondered the mystery of handedness, where the spin of a distant pulsar or the face of a crystal might have tilted the scales toward left-handed life. We have even ventured into ideas that stretch the imagination, from directed messages in our molecules to the sobering possibility of a great filter waiting in the chemical tar pits. This journey reveals a profound truth. The search for the universe's first complex molecules is not merely an academic puzzle. It is the search for our own cosmic ancestry, a quest to understand how the raw stuff of creation became aware of itself. Every theory, from the stochastic soup of the galaxy to the mineral templates on ancient dust, is a different thread in the same grand tapestry, each one attempting to explain how we got here. So now the question turns to you. Which of these 30 pathways sparks your imagination the most? Was it the patient cold chemistry in the void, or the violent forge of a dying star? Do you think the ingredients for life are a universal constant or a rare and precious fluke? Share your thoughts in the comments below. Let us know which theory you find most compelling. If you enjoyed this deep dive into the universe's greatest mysteries, be sure to give this video a like and subscribe for more journeys to the edge of understanding. The cosmos is still writing its story, and we are just beginning